Okay, so welcome now to the fourth video in this workshop on analysis of variance. So hopefully by now you've had success building ANOVA models for between participants designs, and hopefully you've just finished. They're now building ANOVA models for repeated measures designs. So we've looked at repeated measures designs. That's where we've got one factor that's between participants. So each participant appears in only one condition. And we looked at designs where we've got one factor that's repeated measures, where each participant appears in all conditions. And both of these are examples of one-way ANOVA, one-way analysis of variance. What we're going to look at now is factorial ANOVA. And this is for cases where we've got more than one factor. And what we might be interested in is how the factors interact with each other. So if we have two factors, we'll build what's known as a two-way ANOVA. If we've got three factors, a three-way ANOVA, etc. I'm a great believer in keeping experimental designs simple. If your experimental design is simple and straightforward, then your analysis should be simple and straightforward as well. And it's always a good idea, before you actually start data collection, is to figure out how you're actually going to analyze your data. And if the models that you need to build to analyze your data are going to be too complex or will require really tricky interpretation of interaction effects, you probably actually want to simplify your experiment. It's pretty much a far better way to go about doing things. Have a nice, clean, straightforward experiment, hopefully not too many conditions, that will allow you to build a straightforward statistical model to determine whether or not the effect that you're interested in examining is actually present in your data or not. So that's just like a little thing to think about before you run your own work. Always think about the analysis before you even start data collection. So we're going to talk about some, sort of typical or, sort of almost like prototypical effects that we might get when we conduct factorial analysis of variance. So imagine we've got two experimental factors. This is kind of very much in the abstract at this point, but imagine a case where we've got one experimental factor with two levels and a second experimental factor with three levels. So what are the possible outcomes that we might find when we actually build our ANOVA model? So we might find an effect, a main effect of factor one, in other words, a difference between the two levels of that factor. We might find a main effect of factor two, so a difference between one or more of the levels of the three levels of that second factor. Or actually, what we might find is an interaction between the two. So maybe people's performance at level 1 versus level 2 of factor 1 actually varies as a function of the three levels of factor 2. And for this sort of design, it's a 2x3 design, we build a 2x3 analysis of variance, with the first number corresponding to the first factor and the number of levels that it has, and the second number corresponding to the second factor and the number of levels that it has. Okay, so we're going to look now over a few slides at kind of, in a sense, perfect patterns of effects that we might find from this sort of design. So here's a case where we might have a main effect of factor 1, no main effect of factor 2, and no interaction between them. So basically all we have here is a difference between our level 1 of factor 1 and level 2 of factor 1. And this difference is basically the same regardless of what's going on with factor 2. So this is just a main effect of factor 1, no effect of factor 2, and no interaction between the two. Additionally, we might find a case where we've got no main effect of factor 1, so these differences here aren't significant. But we have a main effect of factor 2, so that as we go up the different levels of factor 2, our response variable goes up. But importantly, the difference between our levels of factor 1 and the difference between our levels of factor 2 are independent of each other. In other words, there's no interaction. We could also have a case where we've got a main effect of factor 1, a main effect of factor 2, and an interaction between the two. So we've got a difference between the two levels of our factor 1. And this difference actually varies as a function of the three levels of factor 2. So you can see this difference here. It gets bigger as we go up the levels of factor 2. So this would be a main effect of factor 1. So we've got a main average of a difference between the two levels of this factor, difference between the three levels here. But importantly, we've got an interaction effect. And the interaction effect being significant in this case effectively tells us to ignore the main effects of factor 1 and the main effect of factor 2, because really the story is on how the difference between the levels of our factors changes as a function of the levels of our other factor. We may also have a crossover interaction effect where actually we don't have any effect of factor 1 per se. We don't have any effect of factor 2 per se, but we actually have an interaction effect such that the difference between the levels of factor 1, the polarity actually flips when we look at the differences at each level of factor 2. So we've got a difference here between level 1 and level 2 of factor 1. We've got no difference at level 2 of factor 2, so no difference of factor 1 at this point, but then a flip of the polarity when we look at level 3 of factor 2. So a classical crossover interaction effect. So these are the kind of prototypical effects that we might find. Real world data are rarely as clean as those examples. So imagine this case where we're interested in the effect of positive versus negative contexts and how quickly, in milliseconds, people respond to positive versus negative sentences. So we might think there's a bit of a priming effect going on, where people might be quicker to respond to positive sentences after just seeing a positive context relative to after seeing a negative context. And additionally, people might also be quicker to respond to negative sentences after seeing a negative context relative to after seeing a positive context. Okay, so this is fairly standard priming sort of paradigm. So let's think about this in terms of our design. So we've got two factors. We've got our context factor and we've got our sentence factor. And each of those factors has got two levels. Our contexts could be positive versus negative, and our sentences could be positive versus negatives. So this is a fully factorial design where every participant participates in every condition. So because we've got two factors and each of those factors has got two levels, that gives us 4 possible experimental conditions in total. Okay, so we've got positive context with positive words, positive context with negative words, negative context with positive words, negative context with negative words. Okay, so that's the kind of design that we have. So we're going to read in our data and we're going to inspect the data that we read in. And again, we see we've got two variables corresponding to our two experimental factors, but they're not yet correctly coded as factors in our data frame in R. So we're going to use mutate again to basically convert both our sentence and context variable columns to factors. So we're going to map that back onto a new object, a new variable name that I'm calling factorial data tidied. So if we were to inspect the first 6 rows of that, we'd see that our data frame now accurately reflects the experimental design. So we're going to summarize our data. So we're going to have a little problem that we haven't encountered before, which you may well encounter in real life. So we're doing the same. We're taking our tidied data frame. We're grouping now by 2 different grouping factors, by context and by sentence. And then we're actually generating summary statistics associated with the mean and standard deviation of our dependent variable, which is reaction time. So we get the combinations of our context and sentence factors here. What's going on here? We've got NA values, okay? So we've got our mean and standard deviation fine for the negative condition, and we've got the mean and standard deviation absolutely fine for a positive condition, but we have NA values here corresponding to missing data for our negative and positive conditions. So what's going on? Okay, so R has correctly recognized that we have got missing data. Okay, so anytime you see NA coming up when you're doing some sort of aggregate summary statistics, it suggests that you've got missing data somewhere in your data set. R isn't going to decide for you what to do about those missing data points. So it's not going to do anything, but it's actually going to tell you you've got missing data somewhere, and you need to make a decision as to what you should do with it, okay? There's a really nice function called vismiss that's in the visdat package, and that actually will produce a visualization of our entire data frame, and it will actually tell us if there are any cases where we've got missing data. So if we're actually to take our tidied data frame, factorial data tidied, and put it into the vismiss function, we'd actually see that down here, maybe around about participant 1400 or so, we've actually got some missing data. So overall in the data set, we've got 0.1% of missing data. So we need to do something about that, okay? And what we do is we simply add an extra parameter to our summarize function, and we basically tell R to remove cases where there's missing data. So we set the parameter na.rm to equal true when we're calculating the means, and do the same when we're calculating the standard deviations. So we're basically telling R to exclude those rows where the data are missing. And now we can see we've got a full set of summary statistics pretty much now as expected. Okay, so it can be a little hard to interpret descriptive statistics when you've got factorial designs. I mean, I certainly find it hard to kind of mentally sort of picture what these four different conditions look like and how they maybe relate to each other. So we can do a visualization, but this is a pretty rich data set, and actually it can be quite hard from this visualization to see what's going on as well. If we were to look at the actual sort of summary statistics here. So what did we decide first of all? We decided that we might expect negative sentences to be read more quickly following a negative context and following a positive context. So this is the time here for negative sentences read in a negative context. And this is the time here for negative sentences read in a positive context. And okay, our expectation seems to be held up. The other side was that we thought that positive sentences might be read more quickly following a positive context, which is this point here, than they would be read following a negative context, which is here. And actually here, the difference between that point and that point is only 16 milliseconds, whereas the difference between this point and this point is, 160 odd milliseconds. So we're kind of thinking, you know, there's not going to be a crossover interaction effect here because we'd expect this magnitude to be similar to this magnitude of difference. But there may well be a significant interaction being driven by reaction times to negative sentences. But again, it's kind of hard to see just from the summary statistics and just from the visualization in this case. There's a lot going on here. There's a lot of data points. So we're going to build our analysis of variance model using the same sort of syntax that we used when we looked at using AOV4 in the context of repeated measures designs. But rather than there being just one experimental factor in this case, we've got two experimental factors, and we have to specify those appropriately in our model specification. So context and sentence are our two experimental factors. And we actually specify them in this way. So context asterisk sentence stands for a main effect of context plus a main effect of sentence plus the interaction between these two factors. And because these are both repeated measures factors, we also have to specify them in a random effect term in the same way, so we do that here. So we can build our model. We're going to say in the model as well, we're going to ignore rows, ignore cases where they're missing data points. I think if you don't include this, it's going to throw an error. So we're going to say ni.rm is equal to true. We're going to map the output of this ANOVA model onto our variable model subjects, and then we can ask for our model subjects model to be output in ANOVA format. We're given information about our main effective context, which is it's not significant actually. So we've no main effective context. We've got no main effective sentence, so the F ratio is less than 1. So when the F ratio is less than 1, the effect can never be significant, even with many, many more observations, because that tells us we've got more unsystematic variance in our data than we have systematic variance. But critically, in this case, the interaction effect is actually significant. Our F value is about 4.6, and it's significant at the 0.036 level. So it tells us that we don't have any main effects here, but we do have an interaction effect. One thing I just want to say before we move on is that typically when you conduct analysis of variance, you're going to be treating your participants as your random effect. But within research on language processing, we know that it's actually really important to do analysis of variance where you also treat your items as a random effect too. And the reason we want to treat our items as a random effect is similar to the reason we treat our participants as a random effect. We can never run all members of a population in our experiments. We're building a sample from that population. We're extracting a sample from that population. And it's the same when we're doing research in, say, language processing or any other sort of area where you can't present all possible stimuli to participants. You're actually selecting a sample of stimuli from a population of stimuli. So it's really important in that sort of context to also do what's known as by item analyses of variance. So the analysis of variance models that you'll have built so far will all have been treating subjects as a random effect. These are known as F1 analyses of variance. We can actually run a by items analysis of variance relatively straightforwardly, simply by changing the random effect term. So here we're saying our random effect isn't participants, it's actually items. When you do the mixed models workshop later on, you're actually going to see that within the context of mixed models, you can model multiple random effects simultaneously. Okay, and that's really what you should be doing these days. But for those of you who are familiar with analysis of variance and maybe are using analysis of variance, it's important to remember that typically it's not just a participant random effect analysis of variance you're going to want to build, you're also going to want to build an item one as well. And in the context of the AOV4 function in R, when your data are in long format, where every row corresponds to an observation, it's actually really easy to build that other ANOVA simply by changing the random effect grouping term here from participant to item. Okay, and if we now ask for the output of this F2 analysis, we kind of see nicely the same pattern of results. There's no effect, no main effect of context. It's close, but for all intents and purposes, we can say it's not significant. Although there's a whole debate that I don't want to get into about, I completely agree with the idea that we shouldn't be treating, 0.05 as a cutoff, with things being a bit above that as being non-significant and things being below significant. I mean, that's not how we want to be thinking about things. So we've got a main effect of context that's not too different from the by subject's main effect of context. A sentence main effect that's clearly non-significant, but importantly again, an interaction between the two. So this is a nice example where both our F1 and F2 analyses are basically telling us the same story. There have been cases, certainly within work on language processing, where you'll have a significant F1 analysis of variance, but a non-significant F2 analysis of variance. And typically what that reveals, what that indicates, is that though you've got a strong effect in your data, it's actually being driven just by a small subset of your items. And it may well be the case that there's something special or unusual about that small subset of items which is driving your effect. So it's really important you think about both of these kind of random effect terms in the context of ANOVA. And as I said, it's something we're really going to pay attention to in the context of mixed models. And arguably, in this day and age, you shouldn't be running analysis of variance on your data anyway. If your data are rich enough to support a mixed model analysis, you should be actually building a mixed model to analyze your data. But we'll say a lot more about why that is the case when we get onto the mixed model workshop. So for the moment, just remember, you can do these two different types of analysis of variance. When they tell the same story, that's fantastic. When they don't tell the same story, there are issues. Okay, and you need to figure out what those issues are. So we can go back to our by subjects analysis of variance model to interpret the interaction effect, and we're going to do that in the same way that we've done it previously, using the EM means function in the EM means package. So we're going to take our subjects random effect analysis variance, and we're going to conduct pairwise comparisons by all combinations of our two experimental factors. In this case, we're actually not asking for any automated adjustment of our p-values, because in all of the possible pairwise comparisons that are calculated, so there's 6, only a couple of those pairwise comparisons are actually theoretically meaningful. So when we do research on language, say, we always make sure that when we're examining reaction times to a target, we're also always comparing reaction times to the same target as a function of our other experimental factor. So in this case, we're interested in reaction times to our negative sentences in positive versus negative contexts. So that's like one comparison. And then we're interested in reaction time to our positive sentences in positive versus negative contexts. That's our second pairwise comparison. So in this case, there aren't 6 theoretically meaningful pairwise comparisons to conduct. There are actually only 2. And that's the number that we then want to do a Born-Frone correction over. Okay, so we don't want to automate this. We want to do it manually. And we do it manually by simply multiplying the calculated p-values by 2, because 2 is a number of theoretically meaningful pairwise comparisons. So this p-value here, which is reaction time to negative sentences in negative versus positive contexts, we'd multiply by 2, so it would be 0.0128. And then we'd also multiply this value down here. So without it being corrected, it's 0.7772. This is reaction time for positive sentences following negative versus positive contexts. Because p can never exceed 1, we'd calculate that then to be equal to 1. Okay, so that basically means that we've got an interaction effect that's being driven by negative sentences being read more quickly following negative contexts relative to positive contexts, whereas positive sentences are read at the same speed regardless of whether or not they're preceded by a negative or positive context. So we'd interpret and write up our model, something like this. We'd say we conducted a 2 context positive versus negative by 2 sentence positive versus negative repeated measures ANOVA. So it's important you capture in your ANOVA your experimental design, and we do explicitly like that. So we conducted a 2x2 repeated measures ANOVA to investigate the influence of context valence on reaction times to sentences of positive or negative valence. And the ANOVA revealed no effective sentence. The F was less than 1. So if the F value is less than 1, you don't need to add any more information. No effective context, but an interaction between sentence and context. We report the F values, the P values, and the effect size measure. We then explore that interaction further by saying the interaction was interpreted by conducting Born-Frone corrected pairwise comparisons. This is where we did the correction manually. These comparisons revealed that the interaction was driven by negative sentences being processed faster in negative versus positive contexts. We report then the means for those two conditions. the t-value and the associated p-value of that comparison. And this p-value is the one that we did our manual bond-friendly correction on. While positive sentences are read at similar speeds in negative versus positive context, again, we report the means for those conditions, the t statistic, and the bond-friendly corrected p-value, which we calculated as being 1. So that's how we report, this kind of ANOVA. I just want to finish this final video in this workshop just by saying a few wee things. When you come to write up the results of any ANOVA analysis, it's important to say what type of ANOVA you conducted. Is it between participants, repeated measures, factorial? Make it explicit what factors you had and what labels were associated with the levels of each factor. Report your main effects first and then your interactions. And when you're reporting these things, report your F values, your exact P values, effect sizes, and if possible, your confidence intervals. Always remember that you need to interpret interactions further and you need to follow those up with contrast or more lightly pairwise comparisons. When you have main effects, it's important to say which direction the effect actually goes. And avoid making silly mistakes, which I see people make quite regularly, which is mixing up symbols for less than and greater than, or writing that p is equal to 0.000, which is just a rounding error that you're getting in your output. P can never equal 0.000. If you get in your output p is equal to 0.000, what it's really telling you is that p is less than 0.001. So just avoid those little mistakes when you're reporting your write-up. So in this workshop, we've done quite a lot. We've introduced ANOVA at a very general level. We've talked about why we build ANOVA models rather than conduct multiple t-tests. We've looked at how we build analysis of variance models in the context of between participants designs, where we have different participants in each of our experimental conditions. We've looked at analysis of variance for repeated measures designs, where we've got the same participants in our experimental conditions. In both of those cases, we looked at how we conduct pairwise comparisons with different sorts of corrections to actually determine what's driving significant ANOVA effects. And then in this video, we've looked at factorial designs, probably one of the most common designs, certainly in experimental psychology and many other areas of biomedical life sciences, where we're actually interested not just in the individual factors themselves, but more critically, we're interested in how they actually interact with each other. And we've looked at how we actually interpret those interactions by conducting sort of follow-up pairwise comparisons on the theoretically relevant conditions to really kind of get an understanding of where the differences lie in our data set. So after this video, there's a little bit more for you to do in terms of working through some more stuff on the worksheet. But hopefully this whole workshop will really have given you sort of a good grounding in analysis of variance generally, and specifically has focused on how you build different sorts of ANOVA models in R, so that you're able now to sort of work comfortably in building ANOVA models, interpreting the output and kind of knowing what that output actually means in terms of the underlying story in your data.